Now for section 2.6 on comparison of norms. So the plan is to have a normed linear space and consider two separate norms on the same space. So we'll take linear space X, we'll give it a couple of norms, we'll commonly denote them norms of 1 and norms of 2, and try to relate those two norms to each other and see what implications that has about convergence and topological ideas. So given two norms, norm 1 and norm 2, on a linear space X, we say that norm 1 is weaker than norm 2 if any sequence convergent with respect to norm 2 is also convergent with respect to norm 1. And we'll also say in that case that norm 2 is stronger than norm 1. Now here's a way to interpret that and get an informal grasp for it. Think of strength as the ability to stop sequences from converging. If norm 1 can stop a sequence from converging and norm 2 is stronger than norm 1, then certainly norm 2 can also stop the sequence from converging. There may be, however, sequences for which norm 2 is strong enough to stop the convergence, but norm 1, being weaker, is not strong enough to stop the convergence. So there's sort of an informal way to think about it. The definition is what it is. A convenient way to deal with this more rigorously is given in proposition 2.23. So this quantifies it a bit more. The statement is norm 1 is weaker than norm 2 if and only if there is some k greater than 0 such that the 1 norm of x is less than or equal to k times the 2 norm of x for all x in the linear space. So not the definition of stronger and weaker, but something real useful, something quantitative that doesn't require us to consider convergent sequences. And we'll commonly use this result in proofs. So let's go through and establish that. If and only if claim. So first, suppose such a k exists, where we get this relationship here, and consider x sub n a sequence converging to, say, x with respect to the 2 norm. So we're trying to show the 1 norm is weaker than the 2 norm. If we get convergence with respect to the 2 norm, the 1 norm being weaker, we'll also get convergence. The 1 norm isn't strong enough to stop the convergence. Certainly not if the 2 norm implies convergence. So take epsilon to be greater than 0. There exists a capital N, a natural number, such that when the index is sufficiently large, then we can make, using the fact that x sub n is a sequence convergent to x with respect to the 2 norm. So by making the index lowercase n sufficiently large, we can make the 2 norm of x sub n minus x small. The small we're choosing here is epsilon over k. Remember, k is greater than 0. So make the 2 norm that small using the definition of convergence, and then not a surprise as to what happens next. Then if we take any index lowercase n sufficiently large, greater than or equal to capital N, we'll have that the 1 norm of x sub n minus x is less than or equal to k times the 2 norm of x sub n minus x. I mean, that's the hypothesis here, that the parameter k relates the norms in this way. We're just talking about the norm of x sub n minus x in this equation here. And if n is greater than or equal to capital N, then we get the 2 norm of that vector difference bounded by epsilon over k. The k's cancel. There's the epsilon, and that's exactly the definition of convergence with respect to the 1 norm. All epsilon greater than 0, there exists a capital N, lowercase n greater than or equal to n. The norm of the difference is less than epsilon. So x sub n converges to x with respect to the 1 norm as well. And so any sequence that converges with respect to the 2 norm also converges with respect to the 1 norm. That's the definition of 1 norm is weaker than 2 norm. If and only if result. So let's see, next we need to suppose the weaker condition and extract from that the existence of parameter k. So suppose the 1 norm is weaker than the 2 norm. Define a transformation from, we're treating these as two separate metric spaces, two separate normed linear spaces. They are two separate normed linear spaces. The vector set of vectors is the same, capital X, but in one case we're using a 2 norm, in the other case we're using the 1 norm. So we're defining linear transformation from the metric space, normed linear space. The norm induces a metric, if I can get defensive about that. But the normed linear space X with respect to the 2 norm, map that to the normed linear space X with respect to the 1 norm by mapping X to itself. Okay. So an identity transformation on the set of vectors. We got our reasons for doing this. We're introducing this linear transformation, and we're going to use the norm of this linear transformation to find parameter k. So that's the reason we're doing this first off. You can't argue with the validity of it, though up front it doesn't look terribly useful. So if we'll take x sub n, a sequence converging to x with respect to the 2 norm, that is in this normed linear space, then since the 1 norm is weaker than the 2 norm, we also get convergence of that sequence also to x in the other normed linear space, that is with respect to the 1 norm. Now about the transformation, if we say sequence x sub n converges to x in the 1 norm, and look what we've got here. We've got t of x equals x. So the t parameter, think of that as producing, the t mapping, producing from lowercase x in this normed linear space, produces a tx in this linear space, or t of x. So over here in this space, and that's where we're having this conversation, x sub n approaches x in this normed linear space, we can take the x sub n and replace it with t of x sub n. I mean, it's the identity transformation. We just need to make sure we're doing this in the proper order. Tx, strictly speaking, is not a vector in this space, the normed linear space with the 2 norm. It's a vector in this space with the normed linear space, with the norm being the 1 norm. And that's what we're dealing with here. So take the x sub n, replace it with t of x sub n in this normed linear space. Take the x vector, replace it with t of x also. So we're getting tx sub n approaching tx in this normed linear space. We've chosen an arbitrary convergent sequence in the domain space of t and shown that that's mapped to a convergent sequence in the range space over here. So arbitrary convergent sequence produces convergence of the corresponding sequence when the transformations have been applied. That implies, by theorem 2.1.a, we'll look at that in a second, that t is continuous. So we've shown for an arbitrary convergent sequence, the corresponding function values, transformation values, produces a sequence that converges as well. While we're looking back, we're also going to use the fact that continuous transformations are bounded. And let's quickly recall how we dealt with the norm of a transformation. That's where the parameter k is going to come from. But first, this thing about continuity. Okay, thing about continuity, I think it's here. There we go. Function f mapping x1 to x2. We're in section 2.1, so we're actually treating these as metric spaces, but as commented a while ago, norm linear spaces are metric spaces. The norm induces a metric. So here we got a function mapping one metric space to another. It says it's continuous at a point P in x1 if and only if for each sequence x sub n in x sub 1, which converges to P, we have the limit of the function values, f of x sub n converging to the function value f of P. And that's exactly what we've got. We've got a sequence x sub n, it converges to x in the notation we have in this proof, and the mapping is the transformation capital T. So this gives us continuity at point x. The limit behavior gives us the continuity at a single point. We also mentioned the fact that Theorem 2.6 tells us that if we have continuity at a single point, then we've got a bounded linear transformation. So Theorem 2.6, the fact that 2 implies 3, and the all three of these were equivalent, but the fact that 2 implies 3 leads us next to the conclusion that T is bounded. And finally, for bounded linear transformations, we had this behavior with respect to relating the norm of T of x to the norm of x and the norm of the operator T. We mentioned this when we went through this back in section 2.4. There's actually 3 different norms here. We're mapping, if T maps us from one normed linear space to another, this norm on the left-hand side is a norm in one linear space. On the right-hand side, the norm of x is a norm in the other linear space, normed linear space. And this is the operator norm. So there's actually 3 different norms being used there. The notation there doesn't reflect it, but it does in what we're doing presently, which is this. Okay, so we had that arbitrary sequence converging to x in this space, Theorem 2.1.a, and this observation tells us then that that mapping T is continuous at point x, but continuity implies at a single point implies boundedness, Theorem 2.6. So we'll let K be the norm of that operator, using the operator norm there. And now when we go down here, we'll take the norm of x, the one norm of vector x. That's the same as the one norm of Tx. Tx equals x, right? Tx being a vector in this normed linear space. So we get this equality here by substitution. Note 2.4.a told us that the norm of Tx is less than or equal to the norm of T times the norm of x. And as promised, you can explicitly see there's 3 different norms here. We're getting the one norm over here, and over here we're getting an operator norm and a 2 norm, just like we had in note 2.4.a, but it's more explicit here because we've used notation to distinguish the norms. No subscript on the operator norm, and then these 2 subscripted norms. And we set the norm of T equal to K over there. So we get this equals K times the 2 norm, and that's exactly what we needed. For any x, a vector in the linear space, we've got the one norm of x is less than or equal to K times the 2 norm of x. And that's what we were trying to show. And that's the reason we drug this linear transformation into the conversation. All right, back to 2.6. So we have a way to deal with the stronger, weaker stuff that's quantitative. The existence of some K greater than 0, blah, blah, blah. This idea of stronger and weaker norms is related to the idea, if you've done any topology, It's related to the idea of stronger and weaker topologies, or finer and coarser topologies, they're also called. I've got some introductory topology notes posted online. There's a link to it in these online notes here. And we're about to really relate this idea of stronger and weaker norms to the idea of a finer versus coarser topology on a particular set. When I say topology, I mean the collection of open sets. We don't need a metric or norm, for that matter, to talk about open and closed sets. In a general topological space, you may not have a way to measure distance. It's not a metrizable topological space. But you can still talk about open and closed sets. You do it using the very definition of a topology. Your experience probably has centered to date mostly around defining open and closedness using a metric. We did it in section 2.1 here. Or using a norm that induces a metric. That's sort of what we're in the middle of right now when we were talking about those balls that centered at X with radius R or whatever. So the following relate weaker and normer, weaker and stronger, in proposition 2.24 in terms of existence of open balls. But then these open balls are what can be used to define open sets. And so as a corollary, we'll have weaker and stronger norms related to open sets, which sets are open with respect to those norms, using the kind of the metric space definition of open and closed. So making a transition from stronger and weaker norms to a conversation about open and closed sets, that's totally moving into the topological setting. Proposition 2.24 says, norm 1 is weaker than norm 2 if and only if every norm 1 open ball contains a norm 2 open ball. We'll look at the proof of half of that, but from that it will follow that norm 1 is weaker than norm 2 if and only if, in fact, the 3 statements we've seen so far have been if and only if statements. Every norm 1 open set is norm 2 open. That is, norm 1 weaker than norm 2 if and only if we define openness with respect to, say, norms, or if you like, metrics, or norms induce a metric again. Then we get sets are open with respect to the 1 norm implies these sets are open with respect to the 2 norm. So we're dealing with finer and coarser topologies with this conversation about open sets here versus open sets there in these 2 different normed linear spaces. And it relates to the stronger, weaker ideas of norms. So let's look at a proof of, about half of 2.24. Let's do the only if part. That is, suppose norm 1 is weaker than norm 2, and then we want to show this relationship between open balls. Proposition 2.23, the thing we just did, allows us to discuss a parameter k greater than 0 that relates the norms as given here. So now we've got something quantitative in terms of parameter k. Consider a ball centered at X with radius R, that is the set of all vectors, column Y, in X such that the 1 norm of the difference of X minus Y is less than R. In other words, it's all vectors within distance R of center X, where that distance is determined by the 1 norm. So here's an open ball determined by the 1 norm, an open ball of radius R with respect to the 1 norm. We need to show that contains a open ball of some radius with respect to the 2 norm. It's not surprising that capital K will play a role. We're claiming that this arbitrary ball of center X and radius R with respect to the 1 norm contains this ball of center x and radius r divided by k with respect to the 2 norm. So there's the claim, here's the reason. If we take a vector y in this ball, that is a vector satisfying this condition, think of y kind of as the variable, that is the 2 norm of x minus y is less than r divided by k, that's what it means for y, the vector, to be in this ball, then that implies the following. The 1 norm of x minus y is less than or equal to k times the 2 norm of x minus y. That's ultimately the hypothesis that the 1 norm is weaker than the 2 norm, along with proposition 23 that introduces the k parameter. But we get this 1 norm is less than or equal to k times the corresponding 2 norm. And here we're saying the vector y in 2 norm is 2 norm of x minus y, the distance from x to y, with respect to the 2 norm, is less than r over k. So we get this vector to have 2 norm less than r over k. We've got the k that we picked up earlier, those cancel, you get r. So any vector y that satisfies this also satisfies a condition that the 1 norm of x minus y is strictly less than r. That is, such a y vector also satisfies this and therefore is an element of this ball. So any vector y in this ball is a vector y in this ball. This is the open ball with respect to the 2 norm. That's a subset of the open ball with respect to the 1 norm, arbitrary open ball that we started with respect to the 1 norm. Okay, the text makes just quote the text here, a pretty relevant observation. It says, the space with the weaker norm has more convergent sequences, has bigger closures, has fewer continuous functions from the space, and admits more continuous functions to the space. Think of it in terms of open sets. You can think of it in terms of epsilons and deltas, and all of this should make reasonably good sense. We very much tied this in with the topology on the space. And if we were to compare weaker and, finer and coarser topologies on the same space, we get this similar type of relationship. With coarser and finer versus weaker and stronger for the topologies versus the norms. Not sure if that's respective or not. I'd have to ponder on that, but we get the same kind of relationship when we look at topologies. What we're doing here is the same thing, is dealing with coarser versus finer topologies. 2 norms are equivalent if each is weaker than the other. Now that seems an odd thing to call equivalent. It's maybe even surprising that we could have 2 norms where each is weaker than the other. It's not like a strict weakness or something, I suppose. What we get from the previous 2 observations about the open sets is that 2 equivalent norms on a space have the same open and closed sets. If they got the same open and closed sets, they got the same convergent sequences. Those sequences will converge to the same thing. They'll admit the same continuous functions to and from a space. So the topologies are the same if we have equivalent norms determining openness and closeness. And if we've got equivalent topologies, then we've got basically equivalent analysis stuff. What you do in analysis is you consider open sets and closed sets and limits, continuity of functions. These are analysis kind of things, and they all relate to topology. Final little result from this section says if X is a Banach space with respect to the 1 norm, it's also a Banach space with respect to any equivalent norm. So equivalent norms, I'm looking for a shortcut way to say it. In a Banach space, if In a normed linear space, if you have completeness with respect to the one norm, then you have completeness with respect to any norm equivalent to the one norm. That's the way to deal with the Banach space part. Let's look at a proof of that one. Also, not terribly long. So we're trying to show Banach space with respect to, say, a two norm. That means Cauchy sequences converge with respect to the two norm. So we only need to show that a Cauchy sequence convergent under the one norm is also convergent under an equivalent norm. Let's take the two norm to be equivalent. So let X sub n be Cauchy with respect to the two norm. Proposition 2.3, dealing with one of these norms is weaker than the other. Actually, they're both weaker one than the other. But proposition 2.23 allows us to introduce a k such that the one norm is less than or equal to k times a two norm for any vector x in the linear space. So X sub n is Cauchy with respect to the one norm, given that it's Cauchy with respect to the two norm. We've used this argument before, I think, in the previous section. Look at the sequence. Maybe we'll take X sub n minus X sub m. You know, you can make the norm of X sub n minus X sub m small. You can make the two norm small by making the indices sufficiently large. There exists a capital N, blah, 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 starting with an epsilon argument. But this can be made small. X sub n minus X sub m two norm can be made small by the Cauchiness assumption. X sub n is a Cauchy sequence with respect to the two norm. Well, that means the one norm of X sub n minus X sub m. This is also going to be small. And so this will be a Cauchy sequence with respect to the one norm also. And that's the conclusion. X sub n is Cauchy with respect to the one norm. But we said, with respect to the one norm, we got a Banach space. That means Cauchy sequences converge. So this sequence, X sub n, converges in this normed linear space to something, call it X. But the two norm is weaker than the one norm. Okay, they're actually equivalent, but I can treat the two norm as weaker than the one norm as well, in which case we can draw the conclusion that, hey, if we've got something that converges with respect to the one norm, then it's also going to converge with respect to the two norm. So this sequence X sub n also converges and also converges to X with respect to the two norm. We've actually used, let's see, X2 is weaker than X1. I'm sorry, norm 2 is weaker than norm 1 down here. And we've used norm 1 is weaker than norm 2 up here. So we've used the one is weaker than the other. We've used both of those hypotheses in this. And we're drawing the conclusion that X under the two norm is a Banach space. Let's double check that real quick. Says, where did we start? Right here. Let X sub n be a Cauchy sequence with respect to the two norm. Jumping down here, we concluded that X sub n converges with respect to the two norm. Arbitrary Cauchy sequence with respect to the two norm converges with respect to the two norm. Then that space is complete. So the norm linear space X using the two norm satisfies a condition that Cauchy sequences converge. It's complete. It's a Banach space as claimed. And that takes care of 2.6 with a comparison of norms. We've made it quantitative, brief section, so I like that. Onward next to section 2.7. I will see you there shortly. Have a nice day.